In the previous class, we have gained an insight into the working of continuously tunable dye laser, regarded as one of the most important and popular liquid lasers. And after gas and liquid lasers, the next in line is solid state laser. Beginning from this class, we will explore the principle of working of solid state lasers in the next few classes. As a rule of thumb, the solid state medium that performs as a laser usually has two components: the light emitting atoms, which we will abbreviate as LEA, and a host, passive host, which does not participate in the lasing process, which is often is a crystalline material and occasionally some variant of glass. And these light emitting atoms are actually embedded in the host. These are the light emitting atoms which are embedded in the host. But obvious question that arises is, why do you need such a host for the operation of solid state lasers? You see, the host performs many crucial roles which are instrumental in the operation of solid state laser. First and foremost, it holds the light emitting active atoms firmly in place. And then it allows unrestricted passage of both the pump and the emitted light. You see, the pump light should be able to travel through the host, and as it travels, it interacts with the light emitting atoms, causing their excitation, which is prerequisite for the creation of population inversion. And once the excited atoms emit light, and you have placed this medium, active medium, in which population inversion has been created in a cavity, then this light should be able to oscillate back and forth inside the cavity. So the host must be transparent to this light, and only then there will be amplification of this light inside the cavity through stimulated emission of radiation, and so a part of the light will be emitted as its output. And also there is another important function of this host material. We now know very well that the fraction of the pump energy that is not converted into laser light is eventually realized as heat, and the host therefore must have adequate thermal property to rapidly conduct this heat onto the surface. So these are the three most important roles that the host material plays, and that makes the performance of a solid state laser all right. There exists a bit of ambiguity in naming solid state lasers. See, there exists no well-defined rule for the naming of a solid state laser, and this often results in a great deal of confusion. For instance, the NdYAG, in which neodymium atom is embedded, doped into YAG crystal, and which is one of the most common and widely researched solid state laser, this is often referred to as just YAG laser, while the same YAG can be the host of many more lasers such as polonium, erbium, thulium, etc. So they also can be doped in the same YAG. And while if we say YAG laser, it essentially refers to ND YAG laser. So these are some of the ambiguities. And as a matter of fact, the very first laser, namely the ruby laser, that is essentially a chromium doped alumina, that is chromium doped alumina laser. In this case, this is the host and this is the light emitting atoms. And this is actually named after the natural gem, that is ruby, even though the host here is a synthetic sapphire. So you can appreciate the great deal of ambiguity that is prevalent in naming solid state lasers. And the story doesn't end here though. There is ambiguity. There is also ambiguity in grouping a laser into solid state. Grouping a laser into solid state laser is also no less ambiguous. A glaring example is the case of semiconductor. This is semiconductor in the language of physics is an electronic solid state device that can conduct electric current. A semiconductor laser should therefore be classified as a solid state laser. However, in the context of laser physics, the active medium of a solid state laser is essentially a dielectric, that is the host into which the light emitting atoms are doped, embedded, is a dielectric, and hence it doesn't conduct electricity, unlike the semiconductor. Identifying the semiconductor laser as a solid state laser would thus be truly a misnomer. Now, as the active medium of a solid state laser is essentially insulated, a solid state laser therefore has to be necessarily optically pumped and cannot be electrically pumped because it is insulated. It doesn't conduct electricity. For instance, the ruby laser that Meiman operated in 1960, as you know, was pumped by flash lamp, light emitted by a flash lamp. A semiconductor laser, in the jargon of laser, can, if at all, be called an electrically pumped solid state. It will be appropriate. It will therefore be appropriate to study semiconductor laser independently and should not be clubbed with the general solid state lasers. An elementary knowledge of semiconductor physics is prerequisite to understand the mechanism of creating a population inversion in a semiconductor when it is driven by electric current. We will therefore study semiconductor laser, the most important of all lasers that operate today, separately, and will not combine it with solid state. You see, the discovery of lasing in chromium doped in sapphire, that is the ruby laser, essentially led to a proliferation activity. Why? This essentially was the result of bringing to light more such atom host combinations for achieving amplification of light. A solid has inbuilt ability to provide higher density of active species because they are stacked together very closely compared to a gaseous state, and therefore has the potential to make more powerful lasers. The capability of delivering high power has made solid state lasers indispensable in many applications such as military and industrial, variety of industrial applications for which a very powerful intense beam of light is prerequisite. Solid state laser also has proved quite beneficial in number of medical applications. There exists now a wide variety of solid state laser producing coherent light spanning a remarkably broad area of spectrum. We will soon get to know this. Now, solid state lasers can be grossly divided into two main categories, namely one that basically provides output at discrete wavelengths, so it gives coherent light at discrete wavelengths, and the other variety that deliver tunable output. Now, in the beginning, solid state laser would give only coherent light at discrete wavelengths, and continuously tunable solid state laser appeared later in the scene. Nevertheless, in this course, we will also try to gain a physical insight of the principle of working of continuously tunable solid state lasers. This table gives some example of solid state laser that provides coherent light at discrete wavelengths. As you can see, the active species can vary, can have, there can be number of active species such as chromium, neodymium, erbium, holmium, thulium, etc. And there can be also variety of host materials. However, you can see that neodymium can be embedded in a variety of hosts. And while you can see that YAG can serve as a host material to a number of active light emitting atoms, for example, neodymium, erbium, thorium, thulium, etc. Most of the solid state lasers can be pumped by dart lasers, as you can see. And some lasers can be pumped by both flash lamp and darts. However, the ruby and some glass lasers can be pumped only by flash lamp. And these are the wavelengths, discrete of course, of these solid state lasers. This shows some of the continuously tunable solid state lasers. As you can see, titanium sapphire laser, the light emitting atoms here are titanium and the host is sapphire, it is Al2O3. It provides continuously tunable output over a very wide range, spectral range, from 660 nanometer to 1100 nanometer, almost the red end of the visible light to quite down to the infrared. This can be pumped not by a flash lamp, it can be pumped by another laser. You already know optical pumping is possible by flash lamp as well as by coherent light emitted by a second laser. And the lasers which can be used to pump this laser, say argon ion laser, copper vapor laser, and second harmonic of Nd:YAG laser. Nd:YAG laser gives output at 1064 nanometer. So second harmonic of this will be at 532 nanometer. Even this wavelength also can be used to pump this laser. We will come to this when we study some of these lasers individually. And the other two continuously tunable lasers, which are called Alexandrite and emerald laser, for both of which light emitting atoms, chromium, they produce rather short tunability. So 700 to 825 nanometers and 730 to 840 nanometers. And they can be pumped. The Alexandrite laser can be pumped by both diode and flash lamp, while chromium laser can be pumped only by flash lamp. You see, the methodology of operation, working of all the solid state lasers, most of the solid state lasers are qualitatively similar. Therefore, we, as a representative example, we only consider the working of NDL, which is one of the most versatile and popular and important solid state lasers. However, we know that ruby laser has the disadvantage of being a three-level laser. And in contrast, neodymium laser is a four-level system, four energy level system, and therefore outperform ruby and any other three-level lasers. The low-lying energy levels of both NdR, which is a four-level laser, and ruby, which is a three-level laser, that participate in the lasing process are shown here just for sake of comparison. Now, if you turn your attention to ruby, you will see here that the lower laser level is actually the ground or the source level. This is also the ground level, where initially all the population resides. And this is a three-level system. Therefore, you have to actually, in order to create population inversion, you have to transfer a large amount of ground level population, because this upper level the population is 0, and suppose we have 100 atoms in the ground state, so you'll have to transfer at least 51 so that there is a population inversion, 51 and 49. So transferring such huge number of population from the ground to the upper laser level, of course via the pump level, is indeed a Herculean job. And to maintain this inversion, population inversion in a continuous manner is very challenging. That is why ruby laser would not operate in a continuous mode. It is normally operated in the pulsed mode, as you already know, as you are already aware. And let us now turn our attention to the working of NdR. You see, neodymium atoms have two dominant absorption bands, just like ruby. It also has two dominant absorption bands, 1 and 2. And they can be pumped by light, which is centered at wavelengths around 800 nanometer and 700 nanometer. They can be pumped by light of and around this wavelength. And once the population from the ground state, now you can see that the lower laser level and ground level, they are separated. So lower laser level is practically empty. There is no population in the lower laser. Now, as the atoms are transferred to the pump bands, either this or this, they will quickly drop down to upper laser level, which is a metastable state. Metastable state. And while doing so, part of the excitation energy is actually released, rapidly released non-radiatively to the crystalline lattice. So if the atom is here, excited atom, then if it has to drop down to this level, then this much energy has to be rapidly relaxed, rapidly released to the crystalline lattice. And if it is transiting from this pump level to the upper laser level, then the energy that has to be released is this much energy. The lasing transition occurs at 1064 nanometer in the case of YAG host. When neodymium is doped in YAG, then the emission wavelength is 1064 nanometer. The population arriving at the lower laser level as a result of lasing quickly relaxes to the ground state, again non-radiative way, and becomes available for continuation of the lasing process further. It is now again available for being pumped and continuation of the process of lasing. Now, how do you pump NDR lasers? As you know, historically the pumping of a solid state laser by flash lamp has preceded dart laser pumping by several decades, because in the beginning dart laser did not exist. So in the beginning the solid state laser used to be invariably pumped by flash lamp. However, irrespective of the method of pumping, it would always be advantageous to ensure the most efficient utilization of all the pump photons. The host material is actually a rod shaped, often resembling a small pencil, like this. Therefore, so your host material is a cylindrical tube resembling a pencil in size. Now, pumping this would be using dart laser, that is a laser, that is a pumping source which gives you directed beam of light, would be very quite advantageous, because this light can be easily guided into this, the light can be easily guided into this, and it will have a good spatial overlap with the embedded light emitting atoms. So there will be good spatial overlap. And you can also use a dart laser, choose the wavelength of the dart laser in such a way that there is a good overlap between the wavelength, between the dart laser emission wavelength and the absorption center of the active light emitting species. They will have to absorb light before they emit their own light. So suppose the absorption feature is like this. This is a wavelength, absorption wavelength is lambda 0. So you should choose a diode whose wavelength also should match as closely as possible this. And because dart laser's emission width will be very narrow, it is after all a laser, so its emission width will be narrow, so there will be a good spectral match as well, spectral overlap. So if you use a dart laser to pump a solid state laser, there will be both spatial overlap of the pumping light and the atoms, those are to be pumped, and also spectral overlap, that is frequency matching of the emission of the dart laser and the absorption of this atom. So when a solid state laser is pumped by dart laser, it is expected that it will perform quite efficiently. Now in contrast, thus dart laser has a decided advantage, as it gives out well-directed beam of light having an adequate spectral match with the absorption of the active species. In contrast, the broadband emission of a flash lamp, on the other hand, is non-directional. It emits light in all possible direction around the flash lamp and has also poor spectral match with the active medium's absorption. You see, now consider now the case of a flash lamp. So flash lamp, of course, you cannot put the flash lamp here. We know that the flash lamp has to be pumped through the site. It cannot be pumped, used to pump to the end. So flash lamp will emit light in every direction. So not all the light can be utilized. And to make best use of it, you have to keep this inside a cylindrical enclosure, reflect this light and all such things. But on top of that, the emission width of the flash lamp, it will be much wider. While the absorption feature is just into it, falls quite inside. So, lot of photons, these photons which are here outside this absorption domain would simply stay escape unabsorbed. It cannot be absorbed because there is no frequency matching. This light cannot be absorbed by this because the absorption feature does not match with this frequency. Thus, it is obvious that the pump geometry employed in the operation of a lamp pumped solid state laser differs widely from a dark pumped system. I think I will end here today, and tomorrow we'll begin from different pumping schemes of solid state laser. That is when it is pumped with a flash lamp and how it differs when it is pumped with a dark laser.